Let's take a look at 2013 E&M number 2. This is a circuit with a switch, a resistor, and a capacitor, and then a battery that we can then either connect to the resistor and capacitor or disconnect. And they want us to start out by considering, if we're going to charge the capacitor, where do we move the switch? What we want is to make a complete path that we can trace unbroken through the capacitor and back around to the battery, which means that we need to move the switch to position B. And then what we want to do is measure the voltage of the capacitor. So we need to connect a voltmeter to opposite sides of the capacitor. So one lead from the voltmeter should be to the left of the capacitor, and then another lead should be to the right of the capacitor. Now we're going to take a look at some actual data, which should indicate that we're going to have to make a graph. And what we want to do is find the time constant. And remember, time constant tau from previous notes is resistance times capacitance. And we want to get that off of a straight line graph. Well, we are discharging the capacitor, and if you remember from our derivations from before, discharging the capacitor, we're going to have the voltage as a function of time is going to be the starting voltage and then exponential decay. They did not tell us that we need to derive this equation. So in this case, it is very useful to have this equation memorized because we're going to have to manipulate this equation in order to get a straight line. There are a bunch of options for getting this straight line, and you have to keep in mind that we don't know what RC is. This is supposed to be our slope. It's not going to be our slope if it's in the exponent. So we have to get it out of the exponent so it can be our slope. So rearranging this equation, we're going to have natural log of v at some time t over the original velocity is equal to minus t over rc. And what I did for my numbers is I moved that minus sign over here. So we're going to have minus ln of v over v naught equals 1 over rc. Whoops, that's supposed to be the other side of the parentheses. 1 over rc, and then times t. And we can, if we manipulate our data table such that this whole thing is y, and then this is our slope, and this time is our x. So we have some calculations to do, and what you need to keep in mind is that you just need to make it so that 1 over rc is going to be your slope, and you can have a bunch of options for this. This is just one option. Another option, remember the rules of exponents. If we're dividing the insides, that means, not exponents, rules of natural logs. If we're dividing the insides, that's the same thing as subtracting the natural logs. So, or we could have natural log of v equals minus t over rc plus natural log of v naught. So here we would have y equals mx plus b, and we would have a y-intercept. And what I've done is try to remove the y-intercept by grouping the voltages together. So for my data table, this is going to end up being v naught 252. So I'm going to have minus natural log of v over v naught for my one line here. I'm going to have to end up taking up more space, but we're going to have a 0, 1.23, 2.03, 3.23, and then 3.74 for my minus natural log of voltage at a given time divided by the original voltage. And my x variables are going to be just those times up there. So the two quantities that I'm going to use, and again, you can use other ones. You could use natural log v, or if you want to have a positive slope, you just throw a negative sign at everybody, and there you go. You have this. So option, so B1, what I'm doing is minus natural log of v over v naught is going to be my y, and t is going to be my x. And you can use other options just so long as you get a straight line. Use remaining rows as needed. Well, I've already shown that, and you really only need one row to do that. Oh, by the way, you're also allowed to flip these guys. So you could make t on the y-axis and natural log of v or some combination of these guys on your x-axis. It doesn't matter. What you have to get is a straight line. Now I'm going to pause, erase some things, and scroll down so that I can make a graph. All right, making the graph, and I said that I was going to make the t-axis be horizontal and minus natural log of volt over the original voltage. And again, read the directions carefully. We need to scale and label the axes, including units. So this guy is going to have units of seconds, and this guy is not going to have units because we're going to have volts divided by volts, which is nothing, and then natural log of nothing, and then minus that is still nothing. So this will not have any units. And we need to scale these guys. So across the bottom, we're going to have 10, 20, 30, 40, 50, 60, because the time has to be able to get up to 54. And for the way I've done things, my voltages only have to get up to a little less than 5. So I'll just count by ones here. And this means that across the bottom, all of those guys count by 2, and up the side, all of these guys count by 0.2. And plotting my points, this will be at 6, 0. The second guy will be at 18, 18, barely bigger than 2. 30, no, 18, that's not barely bigger than 2. Sorry. Looking at the wrong row on my handwritten data table. 18, 1.23. So 1, 18.23. It's 30 and barely bigger than 2. 42 and 3 1/4. And then 54 and 3.75. So 3.75. Now I'm going to pause again and try to draw a straight line. This by itself could take me 10 minutes, which is why I need to pause the video. All right, having drawn the line, now we need to find a suitable point on the line, not the data points. So that guy looks pretty good at 42 and 3. And then this guy looks pretty good at 20 and 1.2. So part D, find the value of the time constant. So if you remember, I decided to do V over V naught as Y, 1 over RC times T. That means the slope is going to be 1 over RC. So slope equals 1 over RC equals the time constant is change in Y over change in X. So change in Y is going to be 3 minus 1.2, and change in X is going to be 42 minus 20. So that's going to be 1.8 divided by 22. So the time constant is going to be whatever that turns out to be. Again, since this is a hand-drawn graph, they have to give you some leeway. And I got, oh, wait a second. This is 1 over tau. Sorry, this is 1 over tau. So tau is going to be that guy flipped over. So let me take the reciprocal of that, and that'll be 12.2. So that'll be 12.2 seconds. E part 1. Now they say, oh, by the way, let's tell you what the capacitance is. You tell me the resistor. Well, tau equals RC. So 12.2 equals 1.5 times 10 to the minus 6th R. So take that guy divided by 1.5 micro. Gets us 8.15 million or mega ohms. When I did this by hand on my paper, I got pretty close to the same thing. I got 8.33. So they're looking for something in the neighborhood of 8 million. That's E part 1. All right. Use a dashed line to sketch a possible graph. The capacitance was greater. All right, so if the capacitance is greater, let's go take a look back here at our slope. So if we make C bigger, that's going to make the fraction smaller, and that's going to make the slope smaller. So our dashed line should be rotated to have a smaller slope. Notice it doesn't change the value of the y-intercept. So we're going to have the same slope, and all they want to see is the fact that this line for part E part 2 is lower. So how do we indicate justifying here? Slope equals 1 over RC if C is bigger. 1 over RC is smaller. Whoa, that's supposed to be the eraser. Is smaller. Therefore, shallower line.